Okay. Good afternoon, all. Am I audible? Can you hear me? Am I audible?
Good afternoon, sir. Yes, sir, you are audible.
Okay. Okay. Thank you, Vidhi. Since Krishnamurti sir is not present in this week, that's why I'm taking his class. So this is not my scheduled class actually, so I'm taking this extra class today. So just I'm summarizing whatever so far I have discussed. So I'll be discussing the module that I am discussing or I am taking actually in your section. So in the last class, I have discussed the basics of limit and how to find out the limit for a complex valued function. And when I have discussed how to find out the limit for a complex valued function, I have discussed it comparing with the process of finding out the limit for the function of one variable and two real variables. After that, I have discussed what do you mean by the continuity and how to check whether a function is continuous or not. I have discussed these things also in the previous class. So I have actually shared the total first lecture note of or which is related to the function of complex variable in the Google Classroom. So just you can have a look later on. So today I'm going to discuss the differentiation of the complex valued function and how to check the differentiability of the complex valued function. Okay, so before discussing differentiability of a complex valued function, just I'm sharing my screen. So before that, I would like to ask you a question that what do you mean by the differentiability of a differentiability of a function, and what is the significance of differentiation? Can anyone tell me what do you mean by the differentiation, and what is the geometrical significance of being differentiation of a function? Can anyone tell me? Anyone amongst you? Why do we differentiate a function, and what is the significance? Anyone amongst you can tell me.
To find the slope of a curve, sir.
Sorry, your voice is breaking actually. It is not quite audible.
Sir, to find the slope of a curve.
Okay, slope of a course. That means what is this is the geometrical significance? So from the term differentiation, it is very obvious that we are differentiating a particular thing. That means the overall or entire system is if it is given to us, then we are segregating these in smaller parts and we are analyzing that. That is called by differentiation. So if I consider a function of one real variable, then if a function is given as y equals to fx, so we know that the locus of this function represents a curve. So let's say this is y equals to fx. So if the function is continuous at each and every point, then only the differentiation is possible. So what do we need to do? Just we are trying to draw the tangent. So the slope of the tangent, which you have told, so that is called as the, if this makes an angle theta, then tan of theta is called as the slope. Theta is tangent of close. So slope of the tangent is denoted by the derivative of the function f dash x. So geometrically, what do you mean? Say for example, if we need to differentiate at this point, then we are taking interval around that point. Then this is the functional value. If this is x0, this point is nearer to x0, so this is called as x0 plus delta x. That means we are taking a small increment corresponding to the point in the right hand side. Then we are this is the functional value. So the coordinate of this point, if the curve is y equals to fx, so coordinate of this point will be x0, f of x0, and coordinate of this point will be x0 plus del x, and ordinate will be f of x0 plus del x. So then we are joining this chord, and we are joining this chord. So if this chord makes an angle theta, then also this angle will be theta. So this difference will be del x. That means this is x0 plus del x, this is x0, so that will be del x, and that will be f of x0 plus del x minus f of x0. So this angle and this angle since are same, so tan of this will be same as tan of this. So this is actually f of x0 plus del x minus f of x0 by del x, this one. So if we take this point closer to this point, that means if this point comes closer to this point along this curve, then this del x will gradually come to 0 because this is the length del x. So whenever this will be coming closer to this point, so this length will gradually tends to 0. So limit del x tends to 0 if it exists, then it is defined as f dash x 0. So this is the definition of this is called the first principle of finding out or evaluating the differentiation. So we actually geometrically denote by this, and the significance of this or the definition is denoted as this. So what is the significance of differentiation? So if you are given a curve, then by finding out the tangent, we actually identify uh, the direction corresponding to that curve. If this point is given, you know that whenever we are considering a circular rotation or circular movement, then you know that at any point, if a particle moves along this direction at this particular point, what will be the direction of this particle that is moving along this circular orbit? So along the tangent. At this point, the direction will be along this. So by drawing the tangent, we actually identify the direction corresponding to a particular graph. So since the direction should be unique at each and every point, so if we get more than one value of differentiation at a given point, then we say that the function is not differentiable or derivable at that given point. So whenever the value of f dash x exists, this should exist uniquely. So that is the significance of differentiation. Okay, is that clear or not? So in other word, we can say that here this denotes the change in dependent variable. So while we are changing the independent variable from x0 to x0 plus del x, the corresponding dependent variable will also be changed. So this is getting changed from this point this value to this value. So the change in dependent variable, by change in independent variable, we are considering this quotient, and whenever change in independent variable gradually comes to 0, then this limiting value of the quotient is called as the derivative. So here we are actually measuring the rate of change of the dependent variable with respect to the independent variable also. So these are physical significances of doing the differentiation for function of one real variable. Okay. Now you know that whenever, so if a function is given as y equals to fx, so we are measuring the rate of change of the dependent variable y with respect to the independent variable. So that is denoted as dy dx or f dash x. Now while we are considering the function of two variables, so here since the number of independent variable is 1, so we can measure the rate of change of one dependent variable with respect to one independent variable. But for the function of two real variable, the number of dependent variable is 1, but number of independent variable are 2. So while we are going to measure the rate of change of the dependent variable with respect to two independent variable, then this is not possible for us because, say for example, if I consider if we want to identify any point in space, then we need to know the latitude and longitude. So there's the latitude and longitude. So these are u curves and these are say v curves. Now if we want to identify this point, then by fixing that curve we can vary these curves. So simultaneously we can vary both to identify a particular point. So while we are going to measure the rate of change of z with respect to both independent variable x and y, it is not possible for us to do it simultaneously. That's why while we are measuring the rate of change of z with respect to one independent variable, we need to keep another constant. So y is constant. Similarly, while we are going to measure the rate of change of the dependent variable z with respect to the second independent variable y, then the first independent variable should be marked as constant. So that is called as the partial derivative. So what is the significance of partial derivative? Say for example, while we are considering a function of two variable, so geometrically this represents a surface. So say this is z axis, this is x axis, this is y axis. So here if I draw a tangent, so this will be a tangent plane, this is called a tangent plane. So this will, if I consider a vector in two dimensional plane, so this is a vector in two dimensional plane, you know that we can draw two components along x axis as well as y axis. We can draw two components. Similarly, if we draw a tangent, then along x axis we can get a component, along y axis we can get a component. So along x axis, the component that we are obtaining, that means the tangent parallel, the component of the tangent parallel to x axis is denoted as this, and the component of the tangent parallel to y axis is denoted by this. So in that case, a function of two real variable, instead of one ordinary derivative, there are two partial derivatives, as the number of independent variables are 2 in the case of function of two real variables. So the significance of this partial derivatives are that. That means we are drawing a tangent plane. So this tangent plane have a component The tangent plane has a component along x-axis as well as along y-axis. So the component along x-axis is denoted as del z del x, and the component of the tangent plane along y-axis is denoted as del z del y. So these are the significance. Now we'll be continuing this, or we'll be extending this ideas in order to find out or identify the derivative of a function of complex variable. Is that clear up to this? If you have any kind of doubts, you could ask me. Otherwise, if it is clear, just let me know. Is it clear? Or do you have any doubt? Is it clear or not? Am I audible?
So,
Is it fine? I'm asking for others. I'm uh, asking for from others also. Is that clear or not? Hmm? Is it clear?
yes, it is.
Then I'm moving to the derivative of function of complex variable. So here, if it is a single valued complex function in the domain D defined, so you want to find out the derivative of this function at the point z0. So what is the significance? So you know that we can't actually identify all the four variables that we are actually using in order to identify a function of complex variable simultaneously. Okay. So here, if I consider the independent variable z, so z has two components. One is the real part and another is the imaginary part. And the dependent variable fz has also two components. So one is u, another is v. So what are we doing? We are considering an z eigenplane as the independent plane, and we are considering another plane, that is w eigenplane, as the dependent plane. Then here, what we are doing? We are considering a point P. So the position vector is z0. That means this point P actually denoted by the complex number z0. That means it has the real part x0, imaginary part y0. Now we are considering another point q. So the position vector of q is this, and the complex number z0 plus del z is actually identifying this. So you know that whenever we are considering positional vectors, so these are these are direction oriented. So you know that in a triangle, if this is z0, so that triangle, in the right angle triangle, if this is z0, so if this is z0 plus del z, so this must be this should be del z. So this is z0, this is del z. So this point coordinate of this point q will be z0 plus del z. So you know that whenever we are defining this function fz, so each and every point will be mapped from z plane to w plane, which we are considering as dependent variable here. Sorry, independent variable here must be mapped to certain points in the z eigenplane. So here, let's say this z0 is mapped to w0. So this point that is the image of z0 in the w plane is actually p prime. So if this is w0 means f of z0. So in the same manner, q will also be mapped to certain point in w plane. So that is a q prime. So that is actually w0 plus del w. That is f of z0 plus del z. So this difference would be del w. That means the difference between the dependent variables. So if this happens, then this divided by this, whenever limit del z tends to 0, is denoted by f dash z0 if the limit exists. So what are we doing here? We are considering 2 points P and Q, that is nothing but z0, and increment of z0, that is z0 plus del z. And we know that whenever we are defining a function of complex variable, each and every point will be mapped from z plane to w plane. So the corresponding image of P and Q are P prime and Q prime respectively in the w plane. So the coordinate of P prime is actually w0, that is nothing but the image of z0, so that is denoted by f of z0. Similarly, the image of q is actually q prime in the w plane. So z0 plus del z is mapped to w0 plus del w, that is nothing but f of z0 plus del z. So this difference should be the functional value of del z. That means del of w. That means the difference between the functional value, the difference between the values p dash and q dash. So this by this value by this value, whenever del z tends to 0 is denoted as f dash z0, and that is called the derivative of the function fz at the point z0. Is it clear? Is it clear or not? Can you hear me?
Yes, sir.
Was that clear? Have you understood this? If you have any doubt, without any hesitation, you could ask me.
Sir, please explain this again. How it is coming fz0 plus tailgate minus
Sorry,
fz0.
your voice is breaking. I don't know whether it is my problem from my end or problem from your end. Can you say more louder?
Sir, please explain why it is coming fz0 plus tailgate minus fz0.
Okay, okay, sure. So the coordinate of this point is p prime. So if this coordinate is p prime, so it will be the image of z0. So this will be f of z0, that is w0. So similarly, the image of q is q prime. So that is f of z0 plus del z. So if I consider a right angle triangle here, if this is the Poisson vector, if this is the Poisson vector of p prime and q prime respectively, so this should be this minus this as a vector law, because you know that if I consider the Poissonal vector, so if three vector forms the three sides of a triangle, then this one will be this minus this. So what will be this difference? That is del of w. Del of w means the difference between this minus this. So f of z0 plus del z minus f of z0. So this length will be this one. Is that clear?
Yes, sir.
So if this is not so, then this will not be differentiable. Let's say this value is not becoming the difference between this and this. So this will not be differentiable. It will only be differentiable if this difference is this, and the limiting value of this quotient, this divided by this, gives us the value of dash z0. Okay, is that clear? Okay. Then the properties of differentiability the same as we did for a limit and continuity. So if fz and gz are two functions which are continuous at the point z0, then the sum of two functions will also be differentiable at the point z0. So this will be differentiable, and d dz of fz plus minus gz will be the derivative of fz plus minus derivative of dz. Then if the product of two functions are differentiable, then derivative of product of two functions will be the first function will be fixed, then derivative of the second function, then the second function will be fixed, derivative of the first function. Then derivative of the quotient will also be defined if two are differentiable and g of z is not equals to 0, and the derivative is defined in the same manner, you know, for function of one real variable, that is g of z whole square into g of z into f dash z minus numerator will be fixed into derivative of denominator. So then we need to check the differentiability of the function fz equals to z bar. So if you are asked to check whether a given function is differentiable or not, then you need to take the help of the first principle. You did it for in class 11 also, while you have checked the differentiability for a function of one real variable. Similarly here also, if we are asked to check the differentiability of a given function of complex variable, then we need to check by using the definition. So what is the definition? Our definition is this. So by using this definition, we need to check whether this limiting value exists or not, this function is differentiable or not. So what is z bar? Fz equals to z bar. So the by definition, f dash z equals to limit del z tends to 0, fz plus del z minus fz by del z. If this exists, then only it will be differentiable. So here what we need to do, just we need to check whether the limiting value of this quotient exists or not. If the limiting value of this quotient exists, then it will be differentiable. And if the limiting value of this quotient doesn't exist, then it will not be differentiable. So limiting value will exist if it is path independent. Otherwise, the limiting value will not exist if it is path dependent, and limiting value will exist if it is path independent. So we are approaching towards the path del z tends to 0. So what is del z? Del z means z is x plus del x. So del z will be del x plus I del y. So del z tends to 0 means this tends to 0. Now f dash z is limit del z tends to 0, f of z plus del z. So if fz equals to z bar, so f of z plus del z equals to z plus del z bar. So that is written as z plus del z bar minus fz is z bar by del z. So del z tends to 0 means del z has real part del x and imaginary part del y. So del x del y tends to 0 0. Z means x plus iy and del z means del x plus I del y bar minus x plus iy bar by this del z. Now x plus iy bar means x minus iy and del x plus I del y bar means del x minus I del y, and this will be minus of x minus iy. So x and iy will be deducted. So this will be converted to limit del z tends to 0, that means del x del y tends to 0 0, del x minus I del y by del x plus I del y. Now if this limit exists, then we need to show that if I take arbitrary path, then the limiting value will not depend on that path. And if we can show that if I consider two different paths, then the limiting values are coming different, then at once we can say that the limit doesn't exist. So here we are considering two paths. We are considering one path del y tends to 0. So actually del x del y tends to 0 0. That means we are approaching towards the origin. So we can approach towards the origin through numerous paths. So you can approach towards the origin from x-axis. We can approach towards the origin from y-axis also. So if we approach towards with respect to the path or with respect to x-axis, then along x-axis del y tends to 0. So through x-axis we can approach towards 0 0. So that is del y equals to 0. So then the limiting value will be dependent on del x only. So limit del x tends to 0. If del y equals to 0, this will be 0, this will be 0. So limiting value will be 1. Now through del x equals to 0, that means through y axis, if I want to approach to the points 0 0, that is origin, then del x will be 0. So then the limiting value will be dependent on del y only. So limit del y tends to 0. If del x 0 means minus I del y by I del y. So this will be deducted since del y tends to 0 but it is not equals to 0. So the limiting value will become minus 1. So here once we are taking the path this, then the limiting value is coming as 1. And if we consider this path and approach towards the point del z tends to 0, then we are finding that the limiting value is becoming minus 1. So here by taking two different paths, we are finding that the limiting values are coming different. So at once we can say that the function is not differentiable because the limiting value of this quotient doesn't exist, since the limiting value of this quotient is getting changed whenever we are taking different paths. So the function is not differentiable. Is it clear? Is it clear or not? If you have any doubts, you could ask me. I can repeat this again. Is it clear or not? Am I audible? I don't know whether I am facing any problem today. Can you hear me? Is it clear or not?
Yes, sir.
So these are few problems. I have already shared this note in the Google Classroom, so you can just go through. And if you face any problem in solving those problems, then in the next class you can ask me. Okay. So this is actually all about the differentiability of a complex valued function. Okay. Then today I'll discuss the basics of analytic function. Then for next class I'll be discussing different properties of analytic function. Okay. Can you see the blank screen? Is it visible?
Yes, sir.
Okay.
Yes, sir.
So then today we'll discuss one more thing, that is analytic function. So analytic function is a very interesting topic, a very useful topic while we are studying the function of complex variable. And the concept of analytic function is valid only for the function of complex variable. So while we have studied the function of real variables, either it can be function of one real variable or it can be the function of two real variables. But the concept of analytic function is not valid there. Just the concept of analytic function is valid only for the complex valued function. So what do you mean by the analytic function? So just roughly I'm telling, then I'll be discussing the brief definition. So before that, just tell me, if I give you a function, say for example y equals to fx, a function. So more precisely, if I give you a function, say y equals to x cube. Let's say this is a function y equals to sine x, this is a function, let's say y equals to mod x. So these are all functions of one real variable, that is x, and y is the dependent variable with respect to the variable x. So if I ask you to tell me whether these functions are differentiable in an interval, say I have given interval comma, say 2 comma 3. So there are infinite number of points inside the interval, or I am giving actually a set of real numbers, and I have asked you to tell me whether these functions are differentiable for all real numbers or not. So how we can proceed? Have you understood my question? Say for example, I have given any arbitrary functions of one real variable, and if I provide you a particular point, then you can tell me whether this function is differentiable at that particular point or not by using the first principle. But without asking that, just I am giving infinite number of collection of, or infinite collection of points. Let's say it can be an interval or it can be a set of real numbers. So now I am asking to tell me whether these functions, or how to check whether these functions are differentiable at all real numbers or not. How to verify that, or how we can proceed? Have you got my question? Have you understood what I am asking? Have you understood my question?
Sir, say again.
Sorry,
Sir, please repeat what you said.
I'm telling that, say if I give you a function, say I am giving you a function y equals to x squares, and I'm asking you to tell me whether this is differentiable at point 2, x equals to 2. Then what you can do, just either you can differentiate it and put the value x equals to 2, and if you get a particular value, then you will be telling me that this function is differentiable at x equals to 2. Otherwise you can use the first principle means uh, del x or h tends to 0, f of 2 plus h minus f2 by h. If this limiting value exists, then you will tell me that the function is differentiable at 2. Is that clear or not? Is that clear?
Yes, sir.
Okay. Now, without asking that, if I provide you a collection of numbers, say for example, if I consider this interval, then how many numbers are there? Infinite numbers are there. Infinite real numbers are there. Or I'm giving you an entire set of real numbers. Then I'm asking you to tell me at once whether these functions are differentiable for all real numbers or not. Then how to proceed? How you can verify that? Now is it clear?
Yes, sir.
So how to proceed? Anyone?
If the functions are defined derivable in the two limits, that is 2 and 3, then we can say that the
Okay. So
functions are.
here, if it is in 2n, so but if I give you a set of real numbers, then will you be able to identify what are the two ends?
Yes, sir.
So then how to answer this question, that whether these functions are differentiable for all real numbers, then how we can answer this? So this kind of questions we have faced actually. Everyone listen it carefully because it's a very important thing, because you have studied differentiation, but these are very core thing while you are studying the differentiability of function. You need to know these things. Can anyone tell me? Anyone? Nothing is coming. First of all, just tell me whether all of you have understood what I am asking. Have you understood this or not?
Yes, sir.
So then tell me whatever is coming to your mind. This can be wrong, this can be right. So no matter whether it is right or wrong.
We can take different intervals and then check all.
But infinite intervals will be there too.
Yes.
So if a set of real number is given, it can be set of one real variable or set of two real variables or two real independent variables. Then there is no scope of checking whether it is defined the entire set, entire infinite set. So what do we need to do? We need to take an arbitrary point. Let's say I am taking a point x0. X0 can be any real number. Then I need to check the differentiability of the function at x0. Say what will be the derivative. If you do it by first principle or if you do it directly, you will know that this will be 3x square. Now you know that if I put x as x0, so 3x0 square will be defined for any value of x0 as a real number if we consider. So then we can say that it is differentiable. So what we need to do? Just we need to take or check the differentiability of any function of one real variable pointwise. Without doing it pointwise, at once if a set is given to us, we can't tell whether it is differentiable in the entire set or not. It is not possible at all. So we need to pick a arbitrary point, and at this arbitrary point I need to check the differentiability. If the function is differentiable at that arbitrary point and this is valid for any real number, then at once I can say that this is differentiable. So without checking the differentiability pointwise, it is not possible for us to tell whether this function will be differentiable in the entire set of real numbers or not. Is it clear? Is that clear or not?
We have to take any point, any arbitrary point.
Yeah, you need to take any arbitrary point. Say for example, a 3x x square I have given. So what will be the definition? If I take x0 as the point, limit h tends to 0, f of x0 plus h minus f of x0 by h, say. So here fx is x square, let's say, and there will be limit h tends to 0. This will be x0 plus h whole square minus x0 square by h. So this will be limit h tends to 0. So x0 square will be deducted. So 2x0h plus h square. So this will be h will be common, divided by h by h. So h tends to 0, h not equals to 0, this will be deducted. Now h tends to 0, so that will be 2x0. So we know that this derivative of this exists and this will be x0. Now if I take x0 as any real number, then this will be valid. This is valid for any real number. So I can say that the function is differentiable. The function that is denoted by this is differentiable for any arbitrary real number. So I need to take an arbitrary point, then I need to check it point wise. That means without considering the differentiability point wise, it is not possible for us to tell whether a function is differentiable in an infinite set or not. Is that clear?
Then also we have infinite number of infinite points, so we have to
Yeah.
check for infinite.
So we need to check it for infinite number of points. Now by assuming this is the derivative, you are sure that this will be defined for any real number. So here we can say that this function will be differentiable for any real number. But without checking the point x0, or without taking a particular point, or without taking arbitrary point, it is not possible for us to tell whether it is differentiable or not. Is it clear?
Yes.
But this is possible for function of complex variable, and this concept is defined or denoted as analytic function. But is it saying? Say for example, I am taking a function of complex variable fz. Now a point z0 is given, and if you are asked to check whether this function is differentiable at z0 or not, then what you can do, just you can use this formula, that limit del z tends to 0, f of z0 plus del z minus f of z0 by del z. So if this exists, then we say that f dash z0 will exist, otherwise not. Now if the function is if the function is differentiable at z0, then we can proceed in that way. If this is differentiable at z equals to z0, then we can proceed in that way. Now if I tell that fz is analytic at z0, then this implies fz is not only differentiable at z0, but around z0 we can take a neighborhood where fz is differentiable at each and every point which is there in the neighborhood. So fz is differentiable at the point z0 means fz is solely differentiable at the point z0 only. So I can provide assurance of that. But if I tell that fz is analytic at z0 instead of differentiable, if I use this term analytic, then this implies that fz is not only differentiable at z0, but it is differentiable at each and every point around each and every point around a neighborhood of z0. So instead of this neighborhood, if I take a larger neighborhood, if I take this as a neighborhood, let's say, if I take this as the neighborhood, then if it is analytic at z0, then if I include these points also, this will be differentiable at all these points. That means fz is analytic means we can take any neighborhood around that point, and I can provide the assurance that the function will be differentiable at each and every point which belongs to this particular neighborhood. So not this interval. If I consider a smaller neighborhood, this is differentiable. If I consider any larger neighborhood around z0, then if it is analytic at z0, then it will be differentiable in z0. Is that clear? Is that clear or not? Then how to check whether it is analytic or not, I will discuss later. But fz is analytic at a given point means fz is not only differentiable at that point, but around that point I can consider any neighborhood, and it is analytic at that point means it provides us the assurance that fz is differentiable at each and every point in the neighborhood. Okay, is that clear?
Sir, how to understand a point is neighborhood of Z0 or not?
Sorry.
How to understand a point is the neighborhood of Z0 or not?
Okay, neighborhood means you will denote, because if I consider, say for example, I am telling that a function fz is analytic at z equals to 0, then what can be the neighborhood around z equals to 0? Z equals to 0 means this point. So around that point I can take any circle, and this will be the neighborhood. Say I can take mod z equals to 1. This is neighborhood. So any point which are inside the circle x square plus y square equals to 1, this will be the neighborhood of this point. If I consider mod z equals to 2, that means I am taking 0 0 as the center and radius as 2 unit. So this will also be a neighborhood. So any point which is inside that will be the point in the neighborhood. Is that clear?
That means the domain will be given in the questions, right?
Not domain will be given. If it is analytic, then means you can take any domain, any neighborhood.
Okay, okay.
So that relaxation is there. That means if it is analytic, that means it is more broader concept compared to differentiability, because differentiability means it is differentiable only at a particular point, but analytic means it is not only differentiable at that point, but any arbitrary neighborhood which you can consider, it will be differentiable at all each and every point in that neighborhood. So the neighborhood you can decide as per is, because you know that neighborhood is not unique. Around a point we can take infinite number of neighborhoods. So if it is analytic, that means at all the points in the neighborhood, in any neighborhood, it will be differentiable. Okay.
Okay, sir.
So this is called as the analytic. This function is analytic at a point. Now another concept is there. This is more broader concept compared to this. Analytic in a domain. What does it mean? Analytic in a domain means, So analytic at a point means I am giving only one point z0, and it is analytic at this point means I can take any neighborhood around that point and it is differentiable at each and every point in the neighborhood. Analytic in a domain means I am not taking any point, I am taking a region, a two-dimensional region. This is a domain, let's say D. Now analytic in a domain means I can take any arbitrary points in that domain and the function will be analytic in each and every point in the domain. That means if it is analytic in that point, so this point belongs to this domain. So the function is analytic in that domain means function is analytic at that point also. So that means I can take any interval around that point and it will be differentiable. Similarly, this point also belongs to this domain. So the function is analytic in that domain means function is analytic at that point also. That means I can take any arbitrary neighborhood around that point also, and each and every point in that neighborhood of this given point which is inside that domain, the function will be analytic. So function is analytic at a point means only around that point I can create different neighborhoods and the function is differentiable in that neighborhood. But analytic in a domain means in a domain infinite number of points are there. So the function is analytic at each and every point in the domain. That means corresponding to each and every point which is there in the domain, I can construct any neighborhood and the function is differentiable in that neighborhood. So it is more broader concept because here there is only one point, but in a domain there are infinite number of points. So here it is analytic at only one point, but analytic in a domain means it is analytic at infinite number of points which are inside that domain. Is that clear?
Yes, sir.
Then another concept is analytic in entire complex plane. That means here I am considering only one point. Here I am considering a particular two-dimensional region in the Argand plane Z. So here I am considering the entire Argand plane Z. That means analytic in the entire complex plane means I can pick any complex numbers. Then it will be analytic at that point. That means any complex number I can pick. Then corresponding to that complex number I can create or construct any neighborhood. Then the function is differentiable in that neighborhood. That is more broader concept compared to analytic in a domain. Okay. So fz is analytic at a point means fz is differentiable at every point in some neighborhood of z0. Then function is analytic in a domain means I can consider any point in the domain and around that point the function is differentiable. So another term of analytic function in domain D is called as the holomorphic function in D. Then the entire function. Entire function means the function which are analytic in the entire complex plane are called as the entire functions. Okay. So these are the more broader concept compared to the differentiability of a function. So differentiability of a function is actually indicated as the differentiability of the function at a given point. Then analytic function means in a set or in a neighborhood around a point. Then analyticity in a domain means in the infinite number of points we are considering the function is analytic. Entire function means in any arbitrary complex number the function is analytic. Okay, so these are the definitions. So in the next class I will be discussing how to check whether a given function is analytic or not. Okay.
Sir, which one is more broader?
More broader
Analytic
entire function,
function.
obviously entire function, because analytic function means it is analytic only one point. Analytic function in a domain means in a domain some infinite number of points are there, but they are enclosed inside that domain. Only at those points the function is analytic. Now entire function means any arbitrary complex number I can consider, and at that complex number the function is analytic. So obviously it is more broader compared to this, and this is more broader compared to this. Is that clear? Is that clear or not?
Yes, sir. Yes.
Okay. Okay. So tomorrow I have a scheduled class. So tomorrow I will be discussing the rest of the things. That means how to check whether a function is analytic or not. So this is very useful result or useful term, because this function, this analytic concept, analytic function is only valid for a function of complex variable. So the real variable calculus, whatever you have studied so far, it is not variable. It is not actually valid. So this is a very important concept, because if I know that a function is analytic, then I don't need to check the differentiability of the function point wise. Rather, in the entire set, I could actually tell whether the function is analytic or not.
Hello, sir.
Yeah.
Sir, is there any attendance form regarding this class?
Sorry.
Sir, is there any attendance form regarding this class?
Yeah, I'm sharing the Google IMCRP test. So this is a link, and this is the exam code. So just click the link and provide your full enrollment number and exam code, and complete the class test. Okay. Just someone please check and let me know whether you can access it right now or not. Hey, hey, Ruchiradi, can you access this?
Yes, sir.
Okay. Thank you,
Yes, sir.
Rupam. Thank you, Anupam. So complete the class test. So I'm leaving. Thank you all for attending today's class. So tomorrow at third period, I'll continue from here. Thank you all.